Hello, everyone, and welcome to the innovation track of the Tech Days Munich. Thank you for having me today. I feel honored to share innovation best practices alongside such a diverse and high caliber group of people. Innovation has been a fundamental part of economic growth in the last couple of centuries. The term innovation is everywhere, and people talk about it. But one of the problems that we run into is that the term sounds good, it means something good, but it means kind of everything. And as a result, it means nothing. There is an array of things I could address on this short keynote, but Afton has shown that before we innovate and learn, we need to get into the right mindset. The objective of this short talk is to provide with a world-class tools and frameworks from IDEO to Stanford D School to get you in the right mindset, warm up your brains, and get the juices flowing. This will allow each one of you to capture the most value from the amazing speakers that will follow on this unique and exclusive day. We are briefly going to go over two powerful tools to get you going. The first one is the beginner's mindset. A common issue we encounter very often, mainly when we are working with experienced managers, is that they have been working with the organizations for so long that they have reached a certain level on the corporate ladder. So they feel obligated to navigate the paths that they know and to embrace projects that they can accomplish certain things. They avoid the unknown and to be uncomfortable. This goes back to that we all carry our own experiences, understandings, and expertise with us. Your assumptions may be misconceptions and stereotypes that can restrict the amount of creativity, innovation, and customer empathy you can build with your team and customer. The first step to prevent unconscious bias is to assume a beginner's mindset so that you can approach a transformation innovation challenge with fresh eyes and an open mind. How might we do that? Don't judge. Just observe and engage with users without the influence of value judgments upon their actions, their circumstances, decisions, or issues. Question everything. Question even the things you think you already know and understand. Be curious. Strive to assume a posture of wonder and curiosity, especially in circumstances that seem either familiar or uncomfortable. Find patterns. Look for interesting threads and themes that emerge across interactions with your users and customers. Listen. Really. Lose your agenda and let the scene soak into your psyche. Absorb what users say to you and how they say it, without thinking about how the next thing you're going to say. And the second issue is fail early, fail often. One of the main differences between startups and large corporates, as well as between the US and German culture, is that the former is always learning through failure, and the latter is avoiding failure at all costs. When we talk about innovation, we see failure as experiments that are going to allow us to learn in a controlled environment. Corporate executives avoid stressors all the time, and that only makes their companies fragile. Failure in a controlled environment is an incredibly powerful tool for learning and innovation. This is the approach that led the most disruptive companies in the world, such as Google, Apple, Amazon, Netflix, to achieve success and become leaders in their field and not be disrupted, like many other case studies we all know, such as Xerox, Kodak, and Blockbuster. Failure is an understanding that not all the initiatives are going to work. As we seek to solve big problems, we are bound to fail. But if we adopt the right mindset, we will inevitably learn something from that failure. So on that note, I strongly recommend you guys the TED Talk from Ostro Teller. the captain of the Moonshot Factory. Astro is responsible for steering X projects through the bumps and scrapes they meet along the road to reality. Failure is an inherent part of the process because we'll just never get it right on the first try. In fact, getting right on the first try isn't the point at all. The point is to put something out there in the world and then use it to keep learning, keep asking, and keep testing. In that sense, large organizations should neither wait until everything's perfect to launch, because that means they will fail for good, nor be obsessed with control and ownership when interacting with startups to avoid failure. The obsession with control often leads to corporates buying young startups that are not only just getting traction. It takes them a few years to realize that they don't have the resources and the culture to make those long-term sustainable business. I invite you all to be open and curious, test more and fail often. This will lead to more insights and creativity, as well as to avoid bias. Feel free to reach out if you want to learn more about how to deploy innovation at your organization. That's it for today. Thank you all. I am excited for what's to come next, and please let me know if you want to help the InsurTech Hub Munich build the epicenter of corporate innovation and insurance technology entrepreneurship.
I'm Head of Business Development at Bright AI, and today I will speak about empowering smart cities with deep tech and privacy first. So let me give you some background about the company. We were founded in 2017 in the automotive industry by Hella, and today we are a leading provider of privacy solutions for visual data. In 2018, we were named Europe's hottest AI startup by NVIDIA. In 2019, we won an award as the most innovative ADAS technology by Automotive Tech AD. And we also closed a venture capital round by great investors, eCapital and Giesecke & Devrient. And in 2020, we won the German Digital Award by Handelsblatt and McKinsey. And we had initial projects outside the area of automotive. This will also be the focus of this talk. So what we see when looking at smart cities is that cameras are really the richest sensors to move these intelligent cities forward. And we see that from automotive, so from things like autonomous driving, where vehicles will have 8 to 12 cameras, but also from things like retail, Amazon Go shops and similar concepts, to public transport and existing camera infrastructure that should be used for analytics and insights. Whenever we look at video data being captured in public, privacy is a fundamental concern. And as Tim Cook put it here, people have a fundamental right to privacy. So privacy is not only a topic that is about regulations, that we had a lot of discussions about GDPR in Europe, but it's essentially also a topic of corporate social responsibilities. And do we in Europe want to have the companies that build something for the future? Why is privacy so important, especially for video data in public? One of the reasons is that facial recognition is a growing threat to our privacy. So we know a lot of stories about things, happening in China, about social scores. We see news every day now with the protests going on. So whenever we want to deploy cameras in public, we need to be aware of these risks and to mitigate them to the best possible extent. The solutions that were out there in the past was mainly traditional masking, so things like pixelizing faces or putting black bars on top. The problem with that is that for these innovation use cases that I was showing, these methods will have a negative impact on analytics or machine learning models. And there are even projects where we can see in a quite visual way how there seems to be a trade-off between data privacy on the one hand and innovation at the other. So this is the entrance of one of the train stations in Berlin, and it shows there's one door for no facial recognition and there's another one for facial recognition, and the user can choose. At Bright AI, we see that data privacy and innovation should not be an either-or decision. So what have we built? When capturing video data in public, what you could do is use the original image. In this original image, the identity is not protected, but you could use that data for analytics and machine learning. Now, in the past, there was pixelization, as I showed, and also at Bright AI, we offer a solution that we call precision blur, so a very precise blur for faces and license plates. What we can say about this is that this, of course, makes it hard to re-identify a person or makes it impossible. But the problem is that we cannot use these blurred images for all kinds of machine learning, and usually data scientists don't want to work with that kind of data. So what we came up with at Bright AI is deep natural anonymization, a solution that is based on generative AI. We generate artificial faces and license plates that don't exist, and thereby ensure that the identity of a person is protected, for example, against the threat of facial recognition. But at the same time, you can use these data points that you originally wanted, and you can use that image data, that anonymized image data, as input for training machine learning models. So let me show you an example from public transport to show how this is mitigating facial recognition. So we have here a scene captured on a bus. This is a group of people that I work with, and what you will see now is we take a screenshot of one of these colleagues, and using state-of-the-art facial recognition, in this case a demo by Microsoft Azure, we can try and see, is this actually the same person? So on the left is a reference image, on the right is the original image from the video, and we see, yes, this is the same person. This is pretty impressive from an angle where we wouldn't expect that. Now, we anonymize this footage, and you can see there's masks on top of the people, and this looks also fluent on video data, which is very important for our product. So now, again, looking at that person with the anonymized face, taking a screenshot, and submitting that to the demo site. So you can also see here, this actually looks very different. And by submitting this, we see there is not, this face belongs to a different person. And if now we would do the same thing with a blurred image, the algorithm would say there is no person at all in the image. And this is exactly what would make innovation projects very hard if we would like to analyze blurred images. So deep natural anonymization protects the identity, but still makes sure that you can use this for cases like counting people. So one of the areas where we've deployed this now in the past was with Deutsche Bahn, the German railway company. And the goal here was to create a model to use existing camera infrastructure and then to use people counting models to see how full is a train at a certain point so that people could distribute more evenly on the platform. What we do is we always go into these projects with a privacy-first approach. So before any kind of analytics happens, we need to mask people's faces. And this is so crucial, especially in the future, where maybe someone would like to use some form of facial recognition algorithm. And this is why it's so important to have this as a first step. Also, you don't want to have analytics being done on actual people, but rather on these synthetic faces or identities. Then after anonymizing the footage, there's an analytics module where our customers can select from the best models for the analytics that they need. So there's no login with a certain vendor that will say, okay, we now have a people counting model, we have to deploy expensive cameras, and you're stuck with this. With this solution, with this edge platform, you have the option to select multiple kinds of analytics. And then in the end, there's also a compliance check to make sure there are not too many data points so that in the end you could go back to an original person. So we use concepts like k-anonymity here, which is very crucial. So the advantage is really data privacy first. It's cost efficient because we're using existing camera infrastructure, and it's future proof because we can use the best analytics. Now, showing what these analytics modules mean in case of this DB project. So the first thing, as I mentioned, is measuring the capacities inside the trains. And that was the starting point. Now, due to the COVID-19 situation, it was decided that, hey, how about we can also not only count people, but we can also measure the distance between people. And for that, I also have a short example here. So this is all based on deep learning. This is actually an initial draft, an initial prototype, but it shows that quite accurately with this model, we can, using an existing camera, determine how far are people away from each other. And I think for an initial demo, this is quite impressive. Then, of course, we do this on protected identities, which is very, very important for privacy protection. But also, we would not give the video out, but initially only metadata for sure. So now the third option that we involved in this project now is, are there available seats? So not only a model that counts people, not only measuring the distance, but also detecting whether there are empty seats. And in the future, there could be many more kinds of analytics added, all on this edge device, detecting bicycles or wheelchairs, detecting vandalism. It's just some of the options. Our goal is to protect every identity in public. That's our vision. And if you have any kind of project where public video data is involved, I'm happy to hear about you. I hope you have a great conference. It was great being part of this.
Hello everyone, my name is Jan Alitolpa. I'm working for Nokia Bell Labs in Munich, Germany, and I'm presenting this video on our demo on mobility and quality of service prediction for dynamic coverage optimization, or as we also call it, predictive location-aware network automation for radio. This is work I've done together with Martin Kajo from the Technical University of Munich. So without further ado, let's move to our demo. So what you are seeing here is our simulation environment where we have created a digital twin of the Hamburg Harbor testbed, including then a 3D model of the harbor area and the city itself. And we've also replicated the network testbed deployment in the environment. You can already see a ship starting to move. That's actually a recorded movement trace of the harbor master ship from the real harbor, from the real testbed that we have imported into the simulation. The opaque ship is the ship itself, and the transparent ship you see moving in front of it is actually the prediction from our mobility prediction model, where the ship will go in the next 40 simulated seconds. The simulation is running 10 times real-time speed, so this is why the ships are moving that fast. And now on the background you can already see the Heinrich Hertz Tower, which is where the base station is located of the testbed. On the left, you see the KPIs that we are collecting from the ships. So we will have two ships in this simulation. We introduce one more later. And from both, we are collecting the throughput of the IoT slice, as well as the signal strength measurement, which is the RSRP for the radio environment, and also then the ID of the serving cell. The dark blue line is then the measurement collected from the ship itself, or in this case from the simulated ship. And the light blue line is then a prediction for that KPI coming from our model. Below you see then the configuration of the two cells. So on the left, the transmission power. The orange line is the cell number 1 and the magenta line is cell number 2. On the right you see the beam configuration for the two with the same color coding. So we have 4 beams in each of the two cells. And now the ships are moving west and they're actually approaching the handover region between the two cells. So now you can already see our model is actually predicting. So you see the light blue line jumping before the dark blue line for the serving cell is predicting the handover before it really happens. So we could also use this model for mobility robustness optimization, but in this demo we are demonstrating how it can be used for coverage optimization. Next, ships are moving further west, and on the northern shore of the Elbe River here, there is a high embankment and the buildings that are causing shadowing from the base station. Now you can already see, because of this, actually our model is predicting a radio link failure. So you see the light blue line, that we are losing the serving cell, and also the throughput is predicted to drop to 0, while the dark blue line, which is a measurement coming from the real ship, is not affected. And now the algorithm is already reacting based on the predicted RLF. So you see it's increasing the transmission power of cell number 2, as well as it's down tilting the beam 2 in cell number 2, so that it's pointing exactly to the shadowed area where the ship is predicted to move to. And now you see the degradation is resolved so that the dark blue line, which is the measurement from the real ship, is not affected at all. So the real ship, or the ship itself, experienced no service interruption or degradation at all, because our algorithm reacted already based on the predicted radio link failure. Next, we are introducing a second ship into the simulation to show that our algorithm is not only able to, of course, adapt to one UE moving in the network, but of course it can also accommodate for several UEs, in this case ships moving around the network. And this ship number 2, you can already see also the KPIs we are collecting from it in the chart, is moving south, further away from the base station, so further south in the harbor area. And now simply the long distance from the base station is already causing some challenges for the coverage. And now what you see is that, again, our model is predicting a radio link failure, this time for the ship number 2. So you see the light blue line throughput dropping to 0, and we are losing connection to the serving cell. But our algorithm is already reacting to this predicted failure. So as you see, it's again increasing the transmission power, and this time it's up tilting the beam number 1 in cell number 2, which is the serving beam for the ship number 2, so that the coverage and the range of that beam is extended and it can serve the ship, while the beam number 2 is kept down tilted so that it's still serving the first ship, so the harbor master ship, which is still moving in that shadowed area closer to the base station. And now, as the model is showing and predicting that the service quality for the ships can be ensured, it starts to roll back these optimization actions, because while it's optimizing now the coverage for the IoT slice and for the ships that are using the IoT slice, it may of course compromise then the performance for the other slices. So as soon as these optimization actions or compensation actions are no longer needed by the IoT slice, they are rolled back. And what our predictive model really enables is that we can do these optimization actions only when they are really necessary for the IoT slice, and so improve the overall performance of the whole network. Okay, this concludes this demo video. So thank you for your attention. And if you have any questions, please don't hesitate to contact either me or Martin. Thank you very much.